Share the screen. All right, great. So we are going to create a new Jupyter notebook for this one because it's a bit more code. I don't know what to call this one. I called it initially doors, I think, but it's more like a logical environment for LLMs, right? So let's do new Python. Let's add more cells in here. Let's rename it. Let's just call it game environment. And this, by the way, it's kind of what that latest paper concluded. Use reinforcement learning, just let the LLM do things, and it learns really well. So game environment LLM. How about that? So we're creating that. Right. Close my API tool. So, all right, so I have my Jupyter notebook provided over here already. Transformers, I don't know if it's installed actually, so we may need to install it. Plug that in there. Import torch, and then from transformers, just things for GPT-2. GPT-2 will be something that we're going to use a lot this semester just because of its size and convenience. It's just going to make it easier for doing lots of examples. So it'll be our workhorse starting next week. All right, so I'm going to load these libraries, see if it errors out. And then we're going to create a class to define the LLM agent. So I'm going to copy that one in. All right, it finished, so I guess it is installed. If you don't have it, all you have to do is exclamation pip install transformers, and that should install the library for you. Okay. All right, not hearing any questions, so let's go over this class definition then. So this is just define the LLM agent, class LLM agent. So we're specifying that we want GPT-2. So we're using, of course, Hugging Face and all the models that they have up there. So we're going to need, as we will learn later in the semester, whenever you're using a language model, you need two things. The model itself, which is the weights and the architecture, and then you need the tokenizer, right? So the tokenizer will give you from numbers to words, and then the model will go produce numbers, basically, like IDs, like 3 is the and 7 is cat, right? But the tokenizer should provide that. And it's a bit more complicated than that. So you can see GPT-2 tokenizer, model name. We're going to just download that from the Hugging Face directly. That's how it works. Then GPT-LM head model, so a wrapper, so we can download the model, and now we have it available basically from our constructor here. Then it's a game, and we're going to learn reinforcement learning is very important, but it's basically about games. So if you've ever played chess or you've ever played tic-tac-toe or whatever it is, and that's something we'll need to discuss in a future lecture, there's going to be certain things that you need in there. You need to, in one aspect is you need to keep track of state. Do you see what I'm saying? So you always want to know the state. So the state is the state of the board, right? So if you're playing chess, where's the knight? Where's the rook? Where's the king? That's the state. Okay. And then on top of that, you keep track of things like what action I took before, which is the move. So in board games, it's really nice because left, right, up, down. That's basically it. And then the rewards that you've accumulated. You know, like every time you do something bad, you lose points, let's say. When you do something good, you get points. So there's a reward system going on. This is not the last time we cover these ideas. There's actually a common theme throughout this course because training LLMs is fine-tuning and reinforcement learning, right? So these ideas. So I just wanted to motivate this a little bit with the LLM here and also tie it back to AI agents. So state is going to be some kind of a representation, and it can be complicated. right? So we're going to have to think about that one. So basically here we have, see the action, an output that comes in, and just a tokenizer. So this is just like what processing what the LLM produces until we have the tokens that it produced. So here we have given a state. So here we have the definition, generate an action based on the state. And this is a text-based input because it's an LLM and that's all it understands, words, right? So it's like in chess, I went left, that was my action, and that resulted in the state that now the knight is in this position because I went, so that's the state. And now given that previous action, the current state, I can take another action, you see, and you keep track of all of that. So that's how it works. So state, current state description, and then returns an action, generated action, basically. So I have here the tokenizer, which I instantiated up here, and the tokenizer has to encode. That's what an LLM will do. So it'll take the state, whatever it is, let's say text, right? And it's going to encode it into integers. So that cat is sleeping now becomes a sequence of integer numbers. Okay, and then those input IDs, if you notice, go in here. You specify the length, and several other parameters, and you basically tell the model, okay, given these IDs, generate. Do you guys see that? What does it generate? The output, which is also a sequence of IDs or numbers, integers, 7, 3, 55. If you remember 520, right? We did this with our GPT model. We had our numbers in there. Same thing. And then once we have the generated integers, tokenizer.decode given output. So this should take the integers and give us text, which essentially is the action because it's an LLM and that's how it works. Okay. And then finally, we return the action, and so basically something like the first sentence or whatever it is, right? So some text. So this doesn't fully work, but it gives you the logic of how you would run an LLM in a game environment type of thing. All right. So hopefully that made sense. So that's it. We've created for this game the wrapper around the LLM that we need using something simple like GPT-2. All right. So the next example, next part of this is the environment. So we are playing a game, which means we need to write this logic. Like here, there is no magic library for this. Any game that you create or that you want to play in, you have to, build it yourself, right? So let's take a look at this one. So we're defining a simple text-based environment. And I should say this is only limited by your imagination, right? So we go over here. We have an LLM, and now we need some logic in this game for the LLM to traverse. So the class simple text environment. So we're going to have a state. So these are functions that are really important. Init starts the game, right? So we start at a state. Reset means that we can reset the game. Like whenever you play the game and you just reset to the beginning. Step is a function in games that allows you to take the step. So it takes the current, what does it take? Probably it takes the action. So it takes the action. So once the large language model gets something like a state, produces the next action to perform, then that action goes in the function step of the environment. And so the environment then takes that action and determines the outcome. You see, because the LLM can only say, I'm going to go left or right. But was going left a good idea? That's determined by the environment because that's the rules of the game. Do you guys see that? There could be a lion behind the left door, and you choose left, the lion kills you. So the game determines that. So that's usually how all games work in reinforcement learning and in machine learning. And we will see this more formally a little bit later. So here we have then step takes action, and then this is just some very simple logic just to kind of illustrate that the rules of the game would be here. Okay, so let's break it down. So we initialize the state. So you are in a room with two doors. One door leads to a treasure, the other to a trap. Now I'm using GPT-2. It'd be a nice exercise for you guys, based on everything that you know, to try to use the GPT or OpenAI model with this, because maybe it would understand completely what to do, right, and build something even more complex. All right, reset, same thing. The state resets. So you are in a room with two doors. One door leads to a treasure. The other leads to a trap. Okay. So then we have the step, the action. Take a step in the environment based on the agent's action, where the agent is the LLM. So the action is the agent's action, returns essentially the next state. And this is how it should work. The resulting state, and usually these actually return several things. They return the state because it knows the rules of the game. Then it also gives you the reward. It can tell you if you're done or if you're dead, that kind of thing. So that's how these games work. So it returns the next state, the resulting state after the action, a reward, the reward for the action. Like if you did a good job, then it's going to reward you to encourage you to do better. And then done, which is a Boolean value, whether the episode has ended, such as you won or you died or something. All right, so let's look at the logic. So basically it takes the action, which is text, it makes it lowercase. And this, is just for illustration purposes. If left in action, so you can see like if it said go left, go right, then new state, you choose the left door and found a treasure. The reward is 1. You're done. Else, if right, then in action, then you choose the right door and fell into a trap. And so your reward is -1 and done. True. Else, you are still in the room with two doors, choose left or right, and the reward is 0 and done is false. Do you understand, guys? Not great, but a good illustration of how this works. Okay. And as I said, with this example of GPT-2, it doesn't do that well. But I wonder with other models if it would do better. All right, so hopefully that made sense. So essentially you have the agent over here and some functions, and then you have the environment, which can be as complicated as you want it to be. All right, so once we've done that part, the next part is just to bring everything together and basically to run it and see what happens. So control copy. Okay, so now we're going to talk about the simulation itself of the game. So you can see it's just a function. So we are going to define a function main over here. So the main loop, so the LLM agent interacting with the environment, basically. Okay. So what do we need to do? We need to instantiate the classes for the environment, that's env, and for the agent, that's agent, basically. Then we set the reset state we set the state to end.reset, which basically means you're in the room with two doors. Do you want to go left or right? And then done is false, total reward is 0. So we reset the parameters. Then we print the initial state, which is going to be that you're in a room with two doors. And then it just starts a loop, some kind of a while loop, which is basically while not done. When you're done, you exit out. So the logic is you have the agent who will take in as input the state where you are. You're in a room with two doors and is going to act, right? So agent.act. So let's go over here. So that function agent.act takes in the state and basically just produces an output. So in this case, this is the part that's probably a little bit weak. in this model that would need some improvement, but it will return the action in essence that it should take. That's the goal. And we print it. Then that action goes into the environment to take a step, right? See that there? And then the environment will say what state you're in now because it's the environment. And it provides a reward and if you're done or not. And that's essentially, once you finish that, you set the current state to this next. So the predicted state now becomes the current. And you do that in a loop and you keep tally of the rewards. So essentially in these games, your goal is to maximize the rewards. So you track a graph basically of the rewards going up. That's kind of how you report performance metrics. And this we'll talk about that too a little bit later in the semester. I do have an example for that. Okay, because that will lead us into reinforcement learning through human feedbacks and but we need some background in reinforcement learning. This is just the first example. And that's it. So it doesn't perform so well, but I think I blame GPT-2. All right, there it is. So you can see your first Hugging Face transformers. The plain, simplest example. We'll do some more examples of these BERT models and things like that, just especially because these are the things you can fine tune for your specific. We need to talk about all that. But this should be your first Hugging Face transformers. As you can see, it's kind of big, and this is why I choose GPT-2 and not something even bigger than that. Questions, guys, while it's doing this? No? Huh? Is this related to Q learning? It's a good question. Yes, it is. What's missing here is the Q learning function. Actually, that's what I'm going to cover because you're going to have an environment, you're going to have states, you're going to have rewards, but how do you calculate those rewards? Yeah, so it is going to be related to Q learning. Good question. Huh? Yeah, so there's actually Q learning and then there's deep Q learning, right? So with Q learning, it's just kind of like a table, like a lookup table. And then we can actually represent that table with a neural net. So a function that actually approximates that table. And so that's going to be Q learning exactly. So that's what the upcoming topics are, Q learning, I should say reinforcement learning. And then there's other types of reinforcement learning, policy type of reinforcement learning. And so we'll discuss that a little bit as well. Something called DPO, okay? And then obviously reinforcement learning through human feedback. So the understanding is that you take a large language model, you pre-train it, you fine-tune it, and then you use reinforcement learning for the last part. So that's kind of the pipeline. All right, so still going. Yeah, so I think we may be able to let's see what it does. All right, so let's take while it's doing that, so it's taking a while. So this is what we want to see, right? So I think the environment is solid. It works. It's like any other environment. I just don't know that the model performed as well, GPT-2. So if you guys want to try this, try using Quen, for instance, or something else, just to see if it. The thing is, I can't assign it as a homework yet because I haven't given you enough of the background that you need. But this might be a homework that we do. Is something that I've been thinking. Okay. And it should help you to understand a lot of these concepts. It's just not fully hashed out. All right, so let's see, almost done. And, I remind you, this course is very much big data, so it's going to be a lot of downloads, a lot of memory, and things like that. And Currently, we're just using these models to do inference directly, but eventually when we do fine tuning and things like that, we'll probably have to use the Scholar. Still going, almost done. Almost done. All right, so okay, so initial state there it is. So as you can see, it's running. The simulation ran for a while, and then it just finished. Okay, it's not great, but let's kind of think about what it did. So after we downloaded the model, the LLM, we have it available. We gave it the initial state. You are in a room with two doors. One door leads to a treasure, the other to a trap. So then the agent's action is it received that text and it produced some more text, right? So notice what it did. So this is what I was saying. So remember how it works also, right? From 520, we would give it text and then the output has the prompt, the initial prompt, right? So we give it like some prompt and then it outputs prompt plus more text after. That's just how it works with GPT-2. So we may want to give it the prompt and get what it generates. And then since we know what we gave it, take that out and just keep the rest for this kind of example. Here, it's not so great, but as I said, we can blame GPT-2. You are in a room with two doors. One door leads to a treasure, the other to a trap. So it just started saying the trap is a trap door. The treasure is a treasure. The trap door is a trap door. The treasure is a treasure. You can see that, right? So again, because this is pretty dumb. GPT-2 compared to what we were using earlier, GPT-4 or even Quen is way more intelligent. I think there's llamas now also in Hugging Face, so we can certainly use those. Or we can use Ollama, which we learned about last week, right? So we have lots of options, certainly. But I wanted to keep it simple. All right, so then the next state, this is what it produced, right? So this is the agent's action. So this would go into the environment, and the environment then needs, based on this, to decide what it did. Did it go left or right? Obviously, this output is not great. But the example I provided, all it does is it looks in the action with an if statement. It says, if the word left is anywhere in action, go left. If the word right is anywhere in action, go right. You see that? So it's not great logic, but that's the fault of the environment because it's poorly, just a simple illustration. So here then, based on that, the next state was you are still in the room with two doors, choose left or right. So yeah, so it picked whichever one. What did it? Okay, you chose right. So it basically went to this one, right? So it went to this one. You are still. What is the original state? You are in a room with two doors. Yeah, so there's no word left or right in the initial state. You see that? So when we produce that back out, it wasn't there. You are in a room with two doors. One door leads to a treasure, the other to a trap door. None of those contains the word left or right, which is what we're looking for. Then what we need to do is look at what it produced after. The trap is a trap door. The treasure is a treasure. The trap door is a trap door. None of those include the word left or right. So yeah, you are still in the room with two doors. Choose left or right. Eventually, it did. You are still in the room with two doors. Choose left or right. But because the word left is there, and that's the first if statement, then it just picked left. You see that? So, but that's kind of because this is very simple. So we would have to make this better. One thing is to take out the prompt and just leave the actual output of it. And a smarter model would be also recommended here, and then go from there. Do you guys understand? And then this little framework can be used to basically fine-tune the model and fine-tune the weights. You see that? So that's the idea. So later on with Q-learning, etc., we can see how things can be fine-tuned. All right. And so the conclusion was that it went left, it found the treasure, the reward was given, and so on. So that's it. Any questions? Thanks. So those are the examples I have for this one. We do have about 15 minutes left. Let me see. Let me pause this one.